So I'd like to welcome everybody to Snark Week. Pretty informal week, I think. We have 3 excellent talks I'm excited about, one in a moment, and another on Wednesday by Fantini, and another on Thursday by our own intern Kwang. Other than that, we'll just have some visitors coming through, and I might be pinging you to talk to them, but they're all just people who are really pushing this technology forward. So we're lucky to just have people in the same room this week. So just looking forward to some exciting conversations. Abhiram's going to tell us about HyperNova, which is a significant advance in a particular approach to Snark design called folding schemes. One major benefit of them is keeping the prover's space smaller than pretty much any current approaches, at least that I've seen implementation, and possibly in general. And so he's going to tell us about ideas that have been really influential over the last year or two, and I'm looking forward to hearing the details. So thanks a lot.
All right. Well, thank you so much, Justin. And I'm really appreciate that you guys are putting this together, and especially thank you to Justin for putting together Snark Week. It's a little rare that we're starting to have these opportunities where we all get together and start to really bash out these cool ideas, and feel really this is a great step forward. So I am trying to make this talk just a little bit more high level. We'll see if I actually do achieve that goal or not, with the hopeful idea that later in the week we can maybe dig into the technicals of HyperNova itself. But really, what I wanted to talk about today is, yes, HyperNova for sure, but also the general idea of, how we can start pushing towards practical zero-knowledge virtual machines and where HyperNova falls within that larger landscape. Now, before I begin, I'd like to point out this is joint work with Srinath Setia, my co-author over at MSR. This talk will be roughly divided into 3 parts. In the first part, I'll talk about what a ZK snark is, or a zero-knowledge, succinct, non-interactive argument of knowledge. Now, in short, a ZK snark is a short certificate that proves the correctness of computations without revealing any of the secret inputs to this computation. Okay? And in the second part, I'll talk about zero-knowledge virtual machines, an expressive target application where we consider this idea where we can potentially prove the correct execution of an entire virtual CPU using the power of snarks. And hopefully I'll aim to convince you that this has the opportunity to significantly scale certain aspects of decentralized computing. And finally, in the third part, I'll talk about our own work, HyperNova, which is a performance ZK snark which can be used for applications such as zero-knowledge virtual machines. Now, before I get into the main meat of the talk, I just wanted to give a very quick elevator pitch for the experts in the audience who might just want to get a quick idea of what HyperNova is about. So the core idea with HyperNova is that we effectively design new techniques for proof recursion. And that's this idea that you can write ZK snarks that prove the validity of other ZK snarks. Okay? And we've made a lot of progress in the last 5 years in trying to make proof recursion faster and faster. And HyperNova can be viewed as one of the latest works in this line. Now, in particular, HyperNova designs an efficient new techniques for proof recursion that reduces the overall overhead, especially for computations represented using high-degree constraints. Now, high-degree constraints are useful in practice because they allow us to represent computations more efficiently using fewer but more expressive constraints. And this ultimately leads to more efficient zero-knowledge virtual machines. Now, the core technical piece in HyperNova is something, as Justin mentioned, called a folding scheme, which allows us to take multiple proofs and compress them into a single proof of the same size. And in particular, HyperNova's core technical contribution is to design a new folding scheme for proofs over computations represented using high-degree constraints. And in particular, we can show that HyperNova's folding scheme indeed has a very small recursion overhead that performs favorably when compared to related work, especially in the context where we're trying to fold many proofs over computations represented using high-degree constraints. At a very high level, HyperNova's recursion overhead is dominated by just k group scalar multiplications, where k is the total number of proofs that we're folding, and a logarithmic number of hash operations. Okay.
So what's the, when you say folding and when you say recursion, like what's the relationship between those two? Is folding a specific style of recursion, or how should
Yes, that's a great way of thinking about it. So there's like different ways we can take a proof of like I steps of some computation and recursively convert it into a proof of I plus 1 steps. And folding is one of the latest techniques in trying to do this more efficiently as compared to prior approaches. But roughly, they're all centered around this general nebulous idea of like recursively sort of proving things about things.
Is there like a one-sentence thing of what folding corresponds to in particular, or that'll come later?
Yeah. So what folding does recursively is we maybe have many different proofs, and we recursively compress all these proofs layer by layer into a single proof.
So kind of a tree aggregate.
Exactly, like a tree is a great example. Okay, great question. Okay, so now in addition to the core technical result of HyperNova, which is a folding scheme, we additionally have several additional technical results which augment the core ideas of HyperNova to further improve our techniques for the purpose of virtual machine execution. In particular, in Supernova, we show that it's possible to scale the overall prover running time in a way that only scales with the instruction run at each step rather than the full universal circuit that encodes all instructions. And in CycleFold, we show how to more efficiently modify our folding scheme to more efficiently work with cycles of curves, which are a particular structure of elliptic curves that are used for the particular use case of recursion. And then finally, in HyperNova itself, we show how to take this overall proof of virtual machine execution and blind it at the very end, and thus ensuring that any secret inputs to the virtual machine are not revealed to the final verifier of this proof. But with all of that out of the way, let's get back to the more general part of this talk, which is what is a ZK snark? And then we'll get into what is a ZK VM, and eventually we'll get back into HyperNova itself. Okay, so at a very high level, a ZK snark is a short certificate that attests to correct execution of some function f without revealing some or all of the secret inputs. Okay. Now, as a concrete example, we can imagine this function is something like SHA-256. Okay. And in this particular example, then, we can use a ZK snark to prove that I know a pre-image to a SHA-256 hash without actually revealing what that pre-image is. Now, we can imagine this being used online everywhere today. For instance, if I wanted to log into my banking application, then their servers can just store the hash, and I just have to provide a potentially randomized password, and I don't have to reveal my password directly. Instead, I can just give them a snark proof that I know the password, and that allows me to log onto their servers. So this prevents me from having to move my password in plain text, thus reducing the overall attack vectors. Now, ZK snarks are incredibly exciting because they enable a large class of exciting applications with additional integrity and privacy guarantees. Okay, and today I've put together two examples, one which showcases what ZK snarks can do for online privacy, and another which showcases what they can do for protecting the integrity of online data. Okay, so in the particular case of digital privacy, we can imagine that in near future, where all of us have a digital identity, okay, and this digital identity can have our name, it can have our social security number, it can have our date of birth, it can have additional metadata that's only relevant in the context of online applications. We can of course imagine that such an identity is signed by a trusted authority, such as the US government, and this is what prevents these identities from being spoofed by me. You know, I can't just make up a new identity and show it to some party, okay? But now, given such an object, given a digital identity and given that it's signed by a trusted authority, we can imagine that we can use it in all sorts of applications. For instance, I can file my taxes online, and I can go log into my bank account, and I can vote. All of these things I can do just by furnishing my own digital identity, okay? But there is a key limitation to this particular technology, which is this idea that, well, now I have to start furnishing this identity for less important tasks, like proving my Costco membership, or proving that I'm above 25 so I can get a better insurance premium for a car rental agency, or checking out a library book, right? In all of these cases, I'm stuck with having to reveal my entire social security number, my date of birth, even in applications where it's like not really necessary to show these terms. To get around this issue, we can use ZK snarks, which allows us to prove the necessary properties about such a certificate without revealing any of the confidential information on the certificate for each particular application. Okay? So now, to give you a concrete example, we can imagine, okay, that we write a function, okay, it's called verify age, which all this function does is just check that my certificate is signed correctly and then I'm above 25. And if that's the case, then it will output a new blinded certificate, which only reveals that I'm above 25 and that it has a valid signature, but no other private information about me. At this point, we can use a ZK snark, which will effectively prove that this function was run correctly and therefore prove that this blinded certificate is indeed the result of inputting a valid secret certificate as input. And this ZK snark will reveal nothing about the secret certificate. Okay? So now, going back to our particular application, I can go to a car rental agency and furnish my blinded identity alongside the ZK snark, proving that it is indeed a valid blinded identity, and then they can give me a better insurance premium because I'm above 25 without them having to even check my social security number or even check my age because they know I'm above 25. So now that was a great example for how snarks could be used in the context of private certificates, okay? But they can also be used today for the particular use case of fighting digital disinformation, which is becoming more relevant than ever. You see, in this particular use case, we can imagine that, well, actually, this is actually what's actually happening. So the Associated Press has a strict set of rules for what sort of modifications photojournalists can do on some initial photograph that's signed by some trusted hardware, right? In fact, they're like, okay, all you can do is crop an image, you can recolor it, but that's about it, right? So now the core problem is that, well, if a website, like a news website, wants to serve an image to me, okay, then to prove to me that it's been modified correctly, they probably need to show me the original image and then show me all the modifications they made. So this is maybe dozens and dozens of images along the way. And every time my browser can then check all these images along the way and then check that, okay, indeed, yes, this image does not have any illegal modifications according to the rules of the Associated Press. But this is an issue because this is really cumbersome and slow. Our browsers now need like 10 times the number of like image data being passed around, right? So to get around this issue, we can again use the power of ZK snarks, which can then hide all the intermediate images and just prove that yes, there exists a valid set of images, but you really don't need to look at these images, okay? In particular, how this works is we can imagine that in the future, all of these images are taken by cameras with trusted like hardware inside that signs off on these images, okay? And there's like an authorized signature. And then you can write a computation or a function which only does valid modifications on the original image and also checks the original signature. And then perhaps outputs a correctly modified or validly modified image, okay? And now at this point, we can once again use the power of snarks to prove that this modified image indeed did start off from a valid signed image, okay? And it was permissibly modified along the way. At that point, now we can imagine a future where, if you look at this image in your browser can also check a very quick and short snark proof that the image was indeed generated correctly, okay? And it doesn't need to look at all the intermediate images along the way. So those are just two examples of how today snarks can be used to protect digital privacy as well as digital integrity of data today. And in fact, there's many, many, many more examples of just how powerful snarks can be. They can be used for private voting protocols, private database retrievals. They can be even used to enable private cryptocurrencies, okay? So it's because of exciting applications such as these that snarks are being quickly adopted by both industry and academia and developed by both industry and academia to protect the integrity and privacy of modern applications. So with that, I want to move on to the second part of the talk, which is the particular application of zero-knowledge virtual machines. So what we've been seeing about 5 to 10 years ago is this idea that we can start to converge upon one particular application, which is this idea that perhaps we can prove the entire execution of a virtual machine using a ZK snark. And the core benefit of this is scalability. You see, instead of writing a new zero-knowledge proof system for every new application, instead you can write a zero-knowledge proof system for the underlying substrate running all of these applications. Now, when this idea first came out back in 2013, at least the memory-efficient versions, due to Ben Sasson and others, we simply did not have the snark machinery fast enough to actually make this a reality. But in the last decade, we've made significant leaps forward into making this more and more practical, okay? And the exciting implication of such a technology is that it has the potential to significantly scale certain aspects of decentralized computing. The core idea with decentralized computing is that you have many participants in a network all together running a single global computer. Okay? Now, the way they do this is that they all run the computer locally, and then they check the output state, and then they all vote on what the output state of this computer should be. Right? And you can imagine now that you can run all sorts of secure applications on this computer so long as you trust that the majority of the participants in this network are honest. The core issue with this, however, is that now to run a single computer, you need to replicate the execution of the computer on thousands and thousands and thousands of nodes, which is simply just not scalable. One potential solution for this is that, well, instead of replicating over and over again, we can just have a single participant write a proof of a virtual machine running that particular chunk of that computer, okay? And then send off this proof to every other miner or node in the network, okay? And all of these nodes can then just check that short proof, and then instead of replicated computation, they can just say, okay, well, like the output of this many steps of the computer is this, and then trust that result, and then just keep going and moving forward because they have a snark proof which attests to it, all right? So now the question is, how do we actually build these virtual machines? The direct approach, which has shown a lot of promise recently, is this idea that, well, perhaps all you have to do is take a single cycle of the virtual machine, okay, and replicate it many times, just unroll the entire execution of the virtual machine into a giant trace, and then just use the ZK snark to prove that this trace was actually executed correctly. And this trace can be represented as of a bunch of algebraic or arithmetic constraints. Okay? And it turns out, because of recent work, especially if you're a16z with respect to Jolt, we have that this approach is incredibly fast. What we're seeing is that we can prove almost 17 million iterations of SHA-256 in just 125 seconds. And this is significantly faster than what we knew was possible just half a decade ago. While this approach is great in terms of runtime, it does have a significant memory overhead. Okay? In particular, with current implementations of this direct approach, what we have is that the prover memory also scales linearly with the trace of the entire execution. Okay? And it's a little hard to get the concrete numbers for how much the memory overhead is, but roughly I've measured on my own MacBook Pro that yes, indeed, as we expect, the overall memory overhead does increase linearly over time. What we've seen is roughly, based on our estimates, if we want to prove maybe 100,000 iterations of SHA-256, then this would roughly take a trace that's much, much higher. So now the question is, how can we augment Jolt? How can we improve it even further to maybe handle this memory issue? Okay? And the core idea is that we can use something that's been known for about a decade or two at this point called incrementally verifiable computation. Okay? And this is core idea that, well, instead of globally considering the virtual machine, let's only locally consider each piece of the virtual machine, okay? And locally process it and write a proof. And now, with each additional step of the virtual machine, we can update our proof alongside, okay? So now, with 2 steps of the virtual machine, we can update the proof such as that it does not grow in size, but now is a proof for 2 steps of the virtual machine. And so on and so forth until we have a final proof for the entire execution of the virtual machine that scales with just a single chunk. And indeed, today, using modern techniques, especially from works like Jolt, we can ensure that the proof size and the memory overhead only scales with the latest chunk of execution, while also ensuring that the runtime remains comparable to the direct approach. The story of how we made incrementally verifiable computation or incremental proofs for IVC faster and faster is very interesting in its own right. You see, this idea or the innovations that led to this first started back around 2013, I'll say, by Gennaro and others who showed that it's possible to design a snark that is just constant sized, regardless of the size of the computation it's proving. So, even if your computation is a billion cycles or a trillion cycles or gates or constraints or whatever, what they show is that the proof itself only consists of 7 group elements. Now, if I remember correctly, their proof itself is roughly 288 bytes, just incredibly tiny. Now, using such a proof system, what Ben Sasson and others show back in around 2014, is that they can then use this idea of proof recursion to very efficiently prove at least at the time, very efficiently prove virtual machine execution. Okay? And the core idea back then is that, well, to prove I+1 cycles of a CPU, all you have to do is write a proof of the latest step of the CPU, as well as prove that there exists a proof for I cycles of the CPU. And thus, you can take a proof of I steps and convert it into a proof of I+1 steps, exactly as we need for incrementally verifiable computation. Now, unfortunately, the original approach, due to Ben Sasson and others, was, while it was theoretically elegant, it still wasn't quite practical. And it remained that way for about a decade. And we didn't really know how to do any better than what we had back in 2014, until in 2019, Bogberg and Hopwood introduced a fundamentally new approach towards proof recursion known as proof deferral, where they show how to amortize away some of the overheads associated with recursion. Okay? And at that point, they brought down the number of total constraints of the recursion overhead. So the recursion overhead is effectively the total number of additional computational constraints you need to prove on top of the original proof, or top of the original computation that you're proving for recursion, okay? And they bring that down all the way down to like roughly 250K constraints, okay? Now, given that, this proof deferral approach was fundamentally new at the time, and just over a year, we saw a roughly 5x speed up for the overall recursion overhead. So this was brought down all the way down to around 50,000 gates by Buns and others back in 2021. What we see now is that with Nova, our own work, we saw an additional 5x speed up by introducing this concept known as folding, which showed us that we can take multiple proofs and compress them into the task of checking just a single proof, okay? And now, our own work, HyperNova, can be viewed as taking some of the great ideas from Nova and extending this to high-degree constraints. That means not just quadratic constraints or low-degree constraints, but any constraints. This allows us to represent computations more efficiently for the particular use case of memory-efficient ZKVMs. One other thing I wanted to point out, that this speed-up, I'm only talking with respect to the recursion overhead. Okay? And in particular, when we look at the improvements to the prover runtime as well, per constraint runtime, we see an even bigger differential from where we were just 3 years ago. In particular, for Halo, we roughly had to do about 10 group scalar multiplications per constraint, and this has been whittled down all the way down to just 1 group scalar multiplication per constraint. So putting everything together, we've seen almost 100 times improvement ever since the original approaches back in 2019 due to Bogberg and Hopwood.
This is the prover doing?
This is the prover, yeah. So everything in orange is the prover runtime overhead.
Right.
Yeah. So
and you're saying like the size of the MSM is number of constraints. If that's one, that's what you mean by one. MSM.
Yes.
Okay.
That's what I mean. Yeah. Great question. Any other questions about this particular graphic?
So I'm trying to figure out how to interpret your y-axis. Like,
Yeah.
What is 200,000 constraints a lot or a little? Like,
Yeah. So
you have some fixed computation in mind?
Yeah. 200,000 is, I would say that's a lot. It's like a little hard, again, like to sort of like give an idea for like what's expensive and what's not expensive. But I would say roughly like when we're trying to prove computations, they range from like roughly, like the computation itself ranges from like 1 to like 30,000 gates. So 200,000 is a huge recursion overhead on the original computation we want to prove.
Sorry, the original computation was what were you saying?
So one particular computation is around 30,000 constraints.
30,000.
Yeah. So yeah, 200,000. Just give you very rough like finger in the wind sort of comparison. But also like again, like there's all these improvements with the prover runtime too. So even like even if like 250K gates is cheap in particular application, like the number of proof operations per gate is still quite high in the original approaches.
Was IVC introduced initially for ZKVMs or for some other reason?
No, it was introduced more generally for just recursive applications of a particular function. And ZKVM seems to be the most interesting application right now for IVC. That's a great question as well. For the remainder of the talk, I really just want to talk about HyperNova and the particular details about HyperNova itself, okay? And why it helps us get better and faster ZKVMs. But before I do that, I want to take a quick step back and just really compare and really think about how the field has been moving over the last 10 years based on what we've been seeing so far. So my belief is that snarks today are developing much in the same way the computer architecture developed half a century ago. And the core idea is, well, computer architecture back in the 50s designed specialized hardware for specialized applications. And in much in the same way, in the early 2010s, we were designing snarks for particular applications, such as private database retrievals, secure voting protocols, and private blockchains, and so on and so forth. But what we saw with computer architecture is that, well, in the 60s and 70s, we started developing CPUs for general computation, okay, for general instruction sets, okay? And much in the same way, we started developing snarks for general purpose virtual machines in the late 2010s, okay? And now the great thing about this stage of evolution is that we get significantly more scalable results, right? Because you can conceivably run any program with like very little developer overhead. But the core cost of this is because of the additional abstraction overhead, this is actually just objectively more expensive than the original approaches. So now we're in a stage of development where we're trying to design optimized snarks for the general purpose task of virtual machine execution. Much in the same way where CPUs, we're designing highly optimized architectures for general purpose instruction sets. Okay? And now our own work, SuperNova, HyperNova, and Nova itself, can be viewed as the latest work in this line of optimized snarks for virtual machine execution. So now with that, I want to move on into discussing some of the high-level technical ideas in HyperNova. But before I move on, did you guys have any questions about zero-knowledge virtual machines in general?
Oh, maybe I'll ask this after you introduce HyperNova.
Yeah.
It's like comparison between HyperNova versus just using continuations in Jolt and do a final step of proof aggregation.
I see. Oh, I see. So this continuations approach, is it basically just taking each chunk, writing a proof, and then like having a bunch of proofs and like folding using a tree-like process? Yeah. So I think really this might just be a memory thing. It could be, again, like there's like, you can get rid of some of the recursion overhead potentially with the continuations, but again, like it's like not empirically tested yet. At least I wouldn't know immediately off the top of my head. Okay, so before I explain what folding is, what HyperNova is, like, all the particular techniques specific to us, I want to talk more generally about Valiant's original approach to incrementally verifiable computation. That will help set the stage for what HyperNova changes from the original works, okay?
This is Paul Valiant? There's a lot of Valiants.
I think it's Paul Valiant, yeah. That's a good question. Okay, so to do so, it will help to generalize a little bit. Let's not talk about a single virtual machine cycle. Let's instead just talk about a general function f, okay? Which could be a virtual machine cycle, but it can be pretty much anything else. And now our goal now is to prove recursive iterations of this function f. That is, if you apply f n times to some initial input z0, then you get some output cn, okay? So now the core goal here is how do we take a proof of I steps of f and convert it into a proof of I plus 1 steps, okay? Now Valiant's original approach is incredibly elegant. Basically what he says is that, well, instead of just proving that function f, instead let's prove that function f plus a little bit of extra glue code, okay? And what this glue code is going to do is run a snark verifier. And what the snark verifier will do is check a snark that attests to I iterations of the function f prime. Okay? Now, we know by the nature of snarks, and especially due to construction genera and others, that this snark is succinct. It's only 7 group elements. It's constant size regardless of the computation it's proving. But now what we can do is we can write another snark for the correct execution of the computation f prime. Okay? Just literally take a look at the trace of this computation f prime and prove that indeed it runs correctly. Okay? And we'll call this snark pi I plus 1. Now what pi plus 1 attests to is that, well, the latest iteration of the function f was run correctly, but also that there exists a snark proof of I iterations of the function f prime. And as such, it effectively serves as a proof for I plus 1 iterations of the function f prime. So we've converted effectively a proof of I steps into a proof of I plus 1 steps. Okay? Now, while this approach is incredibly elegant in theory, it turns out that it's still not quite where we want it to be for practical purposes. Now, the core issue is that this forces us to effectively witness the entire trace of the snark verifier inside this trace for the computation f prime when we're writing a proof about its correct execution. Okay? And what that means is that roughly you would have to encode all sorts of complex cryptographic operations, such as pairings and elliptic curve operations and so on and so forth, just using a bunch of addition and multiplication gates. And you can see why that would quickly start to become very expensive very quickly. Now, in fact, when this was empirically tested by Ben Sasson and others back in 2014, when they first designed one of the first ZKVMs based on recursion, what they saw is that, well, okay, using the best SNARK proof systems at the time, this would require roughly 3 pairings, okay, and each of which takes around 20,000 gates, okay, so a total recursion overhead of 60,000. And you might say, okay, 60,000 sounds a little bit cheaper than what Halo was achieving at 250. You have to remember that these pairing-based curves are a lot more expensive, roughly 10 times more expensive than standard elliptic curves, okay? So this really starts to blow up the overall recursion overhead for using or trying to represent a SNARK verifier inside the trace of this computation. Okay, now empirically when this is tested, what Ben Sasson and others found is that the virtual machine itself runs at roughly 0.041 cycles per second, which is incredibly slow when considering native execution, which is currently in the billions of cycles. Okay, so now keeping that in mind, okay, we looked at this and we said, okay, what could we possibly do to make this as fast as possible? That is, reduce the overall recursion overhead, all that additional glue computation you need on top of the original function f to construct the computation f prime.
So just to be clear, so the issue is that the pi's get really big, especially as I gets large?
No, it's not. They all stay the same. Okay. It's just that like the SNARK verifier itself, even though it's constant size, it's very expensive to express.
And where does that show up here? Like
that
shows up in the pi, or?
That's this like verification function right there, that black box. That just gets very expensive. Yeah, it's still constant though. It's just an expensive constant. Yeah.
And yeah, so when you take the verifier and put it into constraints, like that's a lot of constraints.
Yeah.
On top of that, I guess it's the cycles of pairing friendly curves that are 10x more expensive.
Yeah. Yeah.
To make this all work out no worse than Abhiram has already said it is, you need to use special kinds of curves for technical reasons. That's where that 10x is coming from on the slide, which means even once you have these many constraints, proving them is 10 times worse than you think it is, since the prover's doing all these operations over these gross curves.
So in terms of the picture, the chunk of pi I plus 1 that's part of the black box is just kind of a lot of stuff plus like heavy computations involved?
Yeah, that's right. Yep. Okay. Great questions. Any other questions about this particular Valiant's original approach and why it falls short in practice?
Curve cycles, was that introduced by BCTV 14?
Yes, that was indeed there. That's like one of the things that Justin mentioned. Like they showed that to even make Valiant's approach even remotely feasible, we need these like cycles of pairing friendly curves, and even that's still very expensive. So we looked at the original BCTV approach, okay, and we said, okay, well, in the last 5 years, like when I say we, I mean collective as a field, right? And what we realized is that, well, what we could do instead of directly checking these proofs inside the circuit, we know that's expensive, but what we could do instead is perhaps defer the task of checking these proofs. And in particular, Nova introduces a particular abstraction known as folding, which allows us to take a prior proof and compress it into a running proof, okay? In a way that this running proof does not grow in size over time. And what we show is that this compression procedure is significantly cheaper to execute inside a trace or set of constraints than a SNARK verifier, okay? So a little bit more concretely, what we end up doing is to say, okay, well, how about we have 2 certificates, or 2 SNARK proofs. One which proves the latest execution of the function f prime, so f applied to zi minus 1 is equal to zi. And one, inductively, let's assume, that's of the same size, which attests to I minus 1 prior iterations of the function f prime. And you can see that checking these 2 proofs together, when you collect them together, the 2 claims, you have a claim of I iterations of the function f prime, or a proof of that property, okay? And now what we can do is do this compression procedure and take a proof of the latest step and then compress it into running proof to get a new proof, pi plus 1, that's of the same size. Now the core idea here is that, well, checking this new proof is equivalent to checking both prior proofs, and as such, we effectively have a new proof for I iterations of the function f prime. And now on top of that, we can write a new proof for the correct execution of the latest iteration of the function f prime, and now we have two new proofs which now attest to I+1 iterations of the function f prime. So we effectively converted a proof of I iterations of the function f prime, which is these two small proofs, into a proof of I+1 iterations of the function f prime, which is those two small proofs.
And one particular question, you showed before that the difference in performance to BCLMS20 is like 5x compared to Nova.
Oh no, it's BCL. Oh, yeah, that's right.
Yeah,
Yeah.
right. They do like the split accumulation stuff, which is
Yeah.
like roughly similar, right?
Yeah.
Where exactly does the 5x performance improvement come from?
Yeah, so that's a great question. So there's like two things. First, like the folding scheme itself requires fewer group scalar multiplications. Okay, we improved that by a factor of 2. And on top of that, the prover itself to actually participate in the folding scheme needs to do some amount of work, and we improved that by a factor of 2 as well. So we reduce both the folding verifiers work, okay, by a factor of 2, and the folding provers because it needs to do half the number of scalar multiplications. And concretely, adding everything up, they're like concrete costs around like 50K, and ours are like around 10K. So that's like the total 5x. Great question. Yeah.
Is this slide, would it be accurate to summarize it as saying like the Valiant way was sort of proving you verified a snark proof?
Yeah.
And the folding way is take two snark proofs, don't verify them, but smush them into one.
Exactly.
Okay.
Yeah, that's
And
exactly the way to think about it.
The smushing is nicer than verifying the whole thing.
Exactly. That's a great way of thinking about it. Yes.
But you still have to prove that the folding was done correctly, right? No?
Yes. So that's like the elegant part of this, right? So when you are writing a new snark proof, pi+1, okay, that attests to the fact that the function f itself was run correctly and that the previous step of folding was run correctly. So if the final verifier checks the lowercase pi+1, it's checking that folding was done correctly in the previous step as well as f was run correctly, okay? And then now by the folding property itself, if you check this final running proof, capital pi+1, you're effectively checking that all prior folding steps were done correctly. So this is like fundamentally different from this approach of just like taking a bunch of proofs, running the folding scheme, and checking the folding proofs along the way, because the folding proofs themselves are being checked recursively by each of these recursive updates. There is one caveat which I haven't really talked about, which is this idea that if we were to directly fold these snark proofs inside the circuit, that's still a little too expensive. Oh, sorry, when I say circuit, I mean trace. I tried to take all references to circuits here. Okay, so instead of directly folding, what we want to do is instead have short commitments to these proofs. And those are the pieces that's being folded inside the trace. And externally, the actual IVC prover in its own head is taking care to fold the actual underlying openings to these commitments in a similar way. Okay, so that's a sort of minor technical caveat, which is not really important, but like this is sort of the key innovation that started with the split accumulation and so on and so forth. Okay, so now with that out of the way, oh yeah, one more piece I guess is that you can complete the recursion cycle by writing a new commitment to the latest step. Okay, so now with that, the core idea in Nova, effectively, is to show that, well, what we could do is we could design a very efficient folding scheme for an NP complete constraint system known as relaxed R1CS, which we designed specifically for the task of folding two particular statements expressed in this language. Okay, and in particular, what we show is that, well, if you have two relaxed R1CS instance witness pairs, okay, then you can fold it into a single relaxed R1CS instance witness pair that's of the same size and structure and so on and so forth. In fact, what we show that is the recursion overhead, that means all the additional constraints you need to express this computation f prime is dominated by just two group scalar multiplications. And after optimizations and you add everything else together, Nova's overall recursion overhead is just 10,000 constraints. Okay? Now, one other thing is that, like, taking advantage of the 10,000 constraints, we can show that the prover itself is also concretely efficient. In fact, if you want to prove a 1,000,000 gate circuit per recursive step, roughly the prover's runtime corresponds to about a second in each recursive step. So we're getting closer and closer to practical virtual machines. While Nova makes important contributions for allowing us to get faster and faster virtual machines, one of the key limitations in Nova is that it is limited fundamentally, the folding scheme itself is limited to the language of R1CS. And while R1CS is a great, really powerful language, it only supports degree 2 constraints. Okay, and degree 2 constraints, technically you can represent any computation you want using only degree 2 constraints. But the problem is that you need a lot more degree 2 constraints for certain types of computations. So the core idea is that, well, maybe we can try to improve this by building a folding scheme itself that supports higher degree constraints, and thereby allowing us to represent computations more efficiently. And this is precisely one of the problems we tackle in HyperNova, where we show that we can design a folding scheme for a generalization of R1CS called CCS, okay, which supports high degree constraints. The core idea in HyperNova is that we can have a running CCS proof, a proof for computations represented in CCS language, okay, and fold it into a simpler running proof, okay, called linearized CCS, or this running proof is for a language called linearized CCS. And we can keep doing this folding in a way that this linearized constraint system or linearized CCS proof does not grow in size. Okay? And the core idea for doing something like this is to use the sum check protocol, which will allow us to linearize nonlinear constraints into a linear format, which will then allow us to sort of compress it directly into the running linear proof. Effectively, we showed that the recursion overhead for HyperNova is dominated by just one group scalar multiplication as opposed to Nova's 2, and just a logarithmic number of hash operations. So now I want to get into how exactly the folding scheme itself works, but here is like really where it just starts to get really mathematical and like very polynomials and just a bunch of mess. So I'll try to keep it pretty graphical. We can definitely get into the math itself, but I'm going to try to avoid that as much as possible. Now for the experts in the audience, I have placed some of the math inside the black box, but that's really not necessary for understanding here. Okay, so the core idea for our folding scheme, our goal, okay, is to try to take a proof of a computation represented in CCS, okay, and a proof for a computation represented for linear CCS, and then compress them together to produce a new proof of the same format, so a proof of linearized CCS, okay, that's of the same size, that does not grow in size, okay. Now that's the core idea. Now how do we do that, right? And this starts off with this observation that checking this CCS proof is effectively equivalent to checking that a polynomial Q is equal to 0 on a bunch of points, okay? And that's a complex check, but I'll show you in a moment how we can reduce down that check into something simpler. Okay, and then this linear CCS proof, that's actually a lot simpler. Checking that proof is equivalent to checking a bunch of polynomials on the same random point, okay? And these bunch of polynomials are really nice because they're multilinear, okay? They're a lot simpler to check in general. Now the core idea, okay, is that, well, we have a bunch of polynomial checks. Why don't we try to reduce that down to the task of checking just a single giant polynomial? And we'll call that G, okay? So effectively, what we do is we embed the evaluations of Q and the evaluations of L1 and L2 and L3 and so forth into this giant polynomial by effectively embedding them as Lagrange coefficients into this polynomial G. And then we can take a random linear combination of all these coefficients as well to effectively ensure that, you know, instead of checking a bunch of evaluations of G and then checking the corresponding evaluations of Q and L1, L2, and L3, we can instead check over a sum of evaluations of G. So in particular, you know, we get this very complex equation that just embeds all the evaluations of Q and L, but abstracting that all away, really what we're asking is a question about a sum of evaluations for this giant polynomial G. And this is a textbook sum check statement, which basically asks the question, okay, well, prove to me that if you take a polynomial and evaluate it in a bunch of points, then you sum all those points, you get a particular value of v. So for those of you who are unfamiliar, this can be viewed roughly as taking a discrete integral of this polynomial G, okay? So now the question is, okay, what can we do at this point? This is still really a hard question, you know, like, you know, checking a bunch of points on the polynomial G and adding them all together. But this is where the textbook sum check protocol comes in, which is this general protocol or the general system to reduce the task of checking many points on this polynomial G to the task of just checking a single random point on this giant polynomial G. This is still quite a bit too complicated because this polynomial G is very complicated. But what we observe next is that this polynomial G can really be decomposed into a bunch of multilinear polynomials, effectively two sets of multilinear polynomials, such that evaluating these multilinear polynomials at a particular random point R is effectively the same, like, you know, after you get all these evaluations, as evaluating G itself on that random point. Okay, so now we have these two sets of polynomials, and what we observe is roughly the first set is roughly equivalent to checking the original pi CCS, And the second one is roughly equivalent to checking the linearized proof, okay? And the other observation here that's important is that both these sets roughly have the same structure. These polynomials have terms that are similar in certain parts, okay? And then what we can do at this point is by linearity, okay, we can take a random linear combination of the evaluation checks on these polynomials to be just a single set of polynomials. And we'll call that L1 prime, L2 prime, and L3 prime. Okay, and here's where the magic is. Remember at the very beginning, I've mentioned that, well, checking the linearized CCS proof pi is equivalent to checking a bunch of multilinear polynomials on the same point. What we've effectively done here is now reduce the task of checking a bunch of multilinear polynomials on the same point. So now what we can do is just repackage this back up into the task of checking a new updated linearized CCS proof. And we'll call that pi prime LCCS. So now effectively, we've converted the task of checking a CCS proof and a linear CCS proof into a task of checking an updated linear CCS proof. And because we've taken a random linear combination along the way, we've made sure that things do not grow in size. So effectively, the output proof to be checked is equivalent to the size of each of these input proofs to be checked. Okay? So now with that, effectively, that concludes the high-level idea of how HyperNova's folding scheme works. Taking a step back, it's important to note that HyperNova is not the only folding scheme out there, and there's many, many other folding schemes in particular. So we introduced Nova in the spring of 2021 and introduced a full implementation that fall. Okay? And ever since, there's been a significant growth in adoption for this idea of designing folding schemes for the particular application of designing memory-efficient incremental proofs. Okay? And each of these folding schemes, each of them gives different efficiency trade-offs with different benefits. So you can pick the right folding scheme for your particular application. Okay? And it's also important to keep in mind that taking an even further step back, that really this is just another step in this larger picture of trying to design faster and faster zero-knowledge virtual machines. In particular, this idea started back in the early 2010s and kept growing at an increasingly rapid pace until today we're at a point where there's a significant growth in adoption for trying to design snarks for the application of virtual machine execution. Yeah.
What does this HyperNova PCD work?
Oh yeah, so that they didn't really have a name for their system, but it's like a generalization of HyperNova to achieve PCD, where they show effectively how to fold multiple instances at once instead of just two. So the initial version of HyperNova, when we first released HyperNova, we folded two at a time. They show how to fold multiple, and then like multiple instances at a time enables a more general primitive known as PCD, which considers IVC but for arbitrary DAGs, which is useful for distributed computations as opposed to like just VMs.
Jolt, I guess by making heavy use of lookups or offline memory checking techniques, only winds up with degree 2 constraints. Do you have a sense of sort of what that means for HyperNova and the need for high degree constraints?
Sure. That's a great question, right? So like in that particular case, yes, certainly we might not need high degree constraints. Then the key benefit of HyperNova is going from the 2 MSMs to the 1 MSM. So it would just be the prover overhead that we're getting a main benefit from for Jolt. Of course, if you see ways to like leverage high degree constraints, that's all the better because HyperNova definitely supports it, but it's like not necessary to support it to get all the full benefits of HyperNova. Yeah, so I think that's what I would see the benefit of HyperNova versus Nova for Jolt.
Makes sense, yeah. And the I guess another thing it'd be good to, if you have thoughts on, is, so I guess the folding approach looks to minimize like the overhead of recursion, like sort of how much work the prover is doing to prove it, like dealt with proofs correctly along the way.
Yeah.
Rather than proving, that it actually ran the program correctly, sort of useless work.
Yeah.
And something that's not based on folding inherently, although it can hopefully be combined with folding, like Jolt, or pick your favorite ZKVM that's deployed today or something. It doesn't try to just sort of do brute force recursion, not minimizing the overhead of recursion. So I guess the question is, do you just see the two approaches merging together? Do you think that there are benefits of what, like should you just use pure folding when you care about prover space as paramount, and otherwise you should not focus just on overhead of recursion? Just
Yeah.
general-
That's a great question. Yeah, so in general, I would say that like, yes, eventually I do see a future where we use like something like Jolt's front end with like some sort of way to increment proof over time to save on the memories, right? And that could be HyperNova or Nova on the back end. Yeah, so in general, like for shorter programs today, just like using like something like Spartan in the back end of Jolt, that's like perfectly works for like the use cases, for many use cases today, right? But if we want to imagine in the future, we want to improve upon memory, you know, we can use the HyperNova backend. Another question is, you know, like at what point like is the verification overhead actually worth it, right? Because like Jolt's constraints, if I remember correctly, per step is like below 100, like some crazy small number, right? And this is like compared to like the verification overhead of like Nova right now, which is like 10K, right? It's like orders of magnitude more. So where I see these two techniques being like combined is if we get this like approach where we amortize away the verification overhead per many cycles of the virtual machine. So we have like maybe like a 6,000 cycles or something like that. Then we can maybe start using recursion where the verification overhead won't be such a big hit anymore. So finding the right trade-off there, that's a really cool like open question, I think. But I think eventually we'd fall somewhere in that trade-off instead of one end or the other. Yeah.
So these are two ends of a spectrum, and you might not want to be at either.
Oh yeah, I think so.
Does HyperNova comes with zero knowledge, or is it easy to add zero knowledge to
Yeah,
HyperNova?
yeah, that's a great question. Yeah, so this was what I had mentioned early in the second slide or something. Basically, this idea like recursively, HyperNova immediately doesn't come with zero knowledge. We could make it zero knowledge, but what we really need in practice is just you just have a final proof. Okay, and you just want to make that zero knowledge and like maybe compress it even further before giving it to a verifier. And that we've shown can be made zero knowledge. So we add like a zero knowledge layer that proves the knowledge of an IVC proof very efficiently.
I guess there are like still situations in practice where you actually do want the incremental proofs to be published. And there,
Yeah.
if you additionally need zero knowledge,
Yeah.
then is there a simple way?
Yes. So there's several things we're working on right now and try and make it simpler. But the sort of prototypical approach is to sort of use the split accumulation paper introduced. I think it's Buns and others back in 2020. Basically, this is idea that you could like fold in additional like a random instance effectively, and that effectively ensures that your incremental proofs themselves also don't reveal any information about what's going on under the hood. Great question.
Is there more to that? Just getting the final proof rather than the incremental proofs ZK, than using a ZK snark to prove you know the.
Yeah. So it's not as simple as just like throwing your IVC verifier in circuit. So we leverage the fact that the IVC proof itself for us, for HyperNova and for Nova and just the general architecture in general, is basically just a bunch of CCS instances or a bunch of relaxed R1 CS instances, so on and so forth. So we can do some optimizations where we first fold them and then we prove it using Spartan or something like that. So it's a lot more efficient than using universal circuits.
What sorts of cryptographic assumptions you use to build this?
Yeah, so it really just discrete log for both HyperNova and Nova. Basically, we're just using a Pedersen commitment scheme.
And you only get soundness, or because it's a recursion, right? If you want. To
Oh,
get
right.
knowledge
Okay, so
from
you're
it,
talking about like the recursive assumptions as well. Yes. Okay. Yeah, there are several non-standard assumptions associated with recursion as well. Specifically, this is really digging into the weeds, but effectively, like we need to make a non-black box assumption somewhere in there, right? Because this is like a succinct proof of like something that's like non-interactive, right? Non-black box assumption specifically is we have an interactive folding scheme. We prove is knowledge sound, and then when we turn it into like non-interactive, like using Fiat-Shamir's paradigm, we assume that the result is secure. That's the sort of assumption we need to make. Like it's like an instantiating the random oracle assumption. And then we assume that this is like compatible with recursion. So if you have a folding scheme that's like sort of instantiated with the random oracle and that's secure, then you can recurse on top of it and you can still maintain security. Is that the...
So those are still heuristic, even assuming random oracle?
So this is like even deeper into the weeds. You actually can't, like unless you use like very specialized random oracle models, you actually can't prove the security of IVC in the random oracle model, specifically because you need to run the folding verifier inside a circuit. And this folding verifier, once it's inside a circuit, like you can't call a random oracle. So that effectively forces us to have to instantiate the folding scheme ahead of time, instantiate their oracle ahead of time. And this is like fundamentally built into the sort of idea of recursion.
So popping up a level, how
Yeah.
does the community use this kind of heuristic-based, non-standard cryptographic assumption? Well, you get efficiency, that's fine, but
Yeah.
from a cryptographic point of view,
It
are people worried?
Yeah, it varies a lot, I'd say. Some people are like more open to these assumptions and other people are less open to it. What I can say for with certainty is that there is like a lot of exciting research happening right now and like trying to like design like new like models that like are feasible. Like we can believe these models, but we can also prove the security of like things like IVC, like complex cryptographic protocols like IVC inside these models. The real question though is like, can we actually believe these models? Because these are like random oracle models with like all sorts of weird like tweaks to actually make them compatible with the recursion. So yeah, I think maybe the lowest order bit right now though is like exactly as like Halo quoted, like there's like just no known assumptions on no known like attacks on recursion, and like it's like sort of fair, I think, for now, just to assume that like these sorts of heuristic assumptions are safe. We should continue studying them, of course, just like we studied the random oracle model. But I think like it's not going to like break any sort of systems anytime soon, I think.
Just to add to the discussion,
Yeah.
There's a recent work that's sort of overcomes this heuristic instantiation of random oracles.
Okay.
What they did is they just say, well, let's take some hash function. Say it's like correlation intractable with respect to some folding relations, and then you can extract with the folding scheme, like assume you're in the algebraic group model, and then you just extract the witness through that route, and
Is this
not
like-
using random oracles.
I see. Okay. Yeah, we should definitely talk about it then. That sounds interesting.
Yeah. We can
Okay.
talk about that.
Great. Okay. Any other questions?
Yeah, so I think you said even if you just go from Nova to HyperNova and you don't use anything greater than degree 2, I think you said there would still be some performance benefit. Does
Yeah.
that mean you've made like 2 sort of independent improvements to Nova, one in expressibility and then another in
Yeah.
performance?
Yes, so definitely you could view it that way, but fundamentally, like the big change from Nova to HyperNova is we changed the folding scheme, and this folding scheme happens to have multi-dimensional benefits. Yeah, like one is indeed like the overall prover runtime is improved from true group scalar multiplications to just one. So like roughly per constraint, you only have to do one group operation versus 2. And yeah, the other one is like HyperNova more efficiently supports high degree constraints. Now Nova's own folding scheme can be like sort of like extended in like a sort of natural way to support high degree constraints as well, but that would like sort of quadratically blow up the prover runtime and overhead and things like that you don't want that. So HyperNova's like main like goal is to like get rid of these sorts of quadratic blowups and still handle high degree constraints efficiently.